In this module we are going to discuss in depth about one of the most important topic at high frequency wave propagation called as skin depth, or sometimes called as skin effect. Okay, skin effect accounts for all type of major losses in a metallic surface, a metallic waveguide, or an antenna which is made up of a metal but it is driven by some currents at high frequency. There will be loss in the metals because of the skin effect. So understanding skin effect or skin depth is very important if you want to characterize how much loss you are actually able, how much loss you are getting in the metallic materials. Okay, so almost all metals exhibit skin effect. In summary, or in a kind of a overview kind of thing, if I want to tell you in one or two sentences what skin effect is, it simply tells us that at high frequencies when a wave actually falls on a metallic surface, then the wave will not propagate completely inside, it will lie on a small layer called as skin depth layer, and almost all of the currents and the waves are actually concentrated in that small layer, right. Why is that important? Consider a power cable that you are using to transmit power or high voltage from one point to another point. Okay, although this is not the high frequency effect, the effect is essentially the same because of the lengths that are involved. Okay, what happens is that the entire electromagnetic energy is concentrated on this very small surface. Okay, and this surface of this thickness is actually called as the skin effect. Okay, so the entire electromagnetic field is actually concentrated on this outer or just slightly inner conductor and only in this particular region. Okay, this width is called skin depth. Almost all the current is concentrated in this skin depth. So if you were to actually take a copper cable and consider a certain radius of the copper cable, then what you see is that the only usable area of this copper cable is around the skin depth. Okay, and all the other areas of the copper that you have used is actually not carrying any current at all. Okay, this is especially true at high frequencies. So what is the job of this extra copper? The extra copper is only giving you mechanical stability. So if you want to actually have a trade-off between how much mechanical stability you want versus how much copper you use, because you know that the electromagnetic fields are all concentrated on the skin depth on the outer to inner layer of the copper. So it's the question as to how much copper can you actually afford to waste. Okay, you can make a mile long or a mile diameter uniform copper rod to carry electromagnetic energy, but that would be totally useless because the electric fields would only be around a small region, and we will just very quickly estimate what is the order of magnitude of that one here, and that order of magnitude you will be surprised to see the value out there. So in that small region is what the entire electromagnetic waves are concentrated on. Therefore it does not make sense to use so much of copper to fill in between, except if you are looking for mechanical stability. Alright, with this thing in mind, let us try to see what this skin depth is. Okay, now we have already encountered what skin depth is, right. So we have already written down an expression for skin depth and we denoted that one by a Greek letter delta. Okay, this was supposed to represent your skin depth and it is given by pi f mu sigma. Okay, for a copper, sigma is in the order of 10 to the power 7 per ohm meter and mu is equal to 10 to the power minus 7 Henry per meter. This is for the case of mu is equal to mu 0, which is what we are going to assume. And if you substitute these values of for mu and sigma, the actual sigma is around 5.9 into 10 to the power 7 or something. So if you substitute all these values, you will get delta to be around 0.067 divided by square root of f, where f is the frequency measured in hertz. Okay, so you can actually plot this, okay, in the form of frequency along the horizontal axis and the skin depth in micrometers along the vertical axis. Okay, and you can employ, rather than talking in terms of linear scale for f, you can employ a log scale. Okay, I have about 10 to the power 9, 10 to the power 10, 10 to the power 11, and what you will see is that at frequencies which are close to kilohertz or less, the skin depth is around 1000 microns. Okay, 1000 micrometer is nothing but 1 millimeter, right. So this is about 1 millimeter thick even at frequencies as low as 1 kilohertz. Okay, this value drops down to about 0.1 micron at around 1 gigahertz, okay, or rather at around 10 to the power 11. So at 1 gigahertz you are very close to 1 micrometer. So this is the skin depth that you are looking for copper at a frequency of 1 gigahertz. So if you were to build up your PCB with and populate it with gigahertz sources, then this is essentially the region or the thickness of the copper that is being penetrated because of the skin depth. Okay, even though these currents are concentrated in this very small region, the kind of losses they induce cannot be neglected. Okay, so even though they might be propagating only in a short layer around the conductor, you cannot actually ignore the losses of because of this one. We will going to come back to this losses in a short while. Okay, so let's look at certain equations which will describe skin effect for us. Okay, to describe skin effect, I actually need to write an equation for current density vector J. Okay, to write an equation for current density vector, I actually start from an equation which I have for electric field, which is del square E is equal to j omega mu sigma plus j omega epsilon into E. Okay, and because this is a good conductor, skin effect is observed in those good conductors. Sigma is very large compared to omega epsilon. Therefore, you have del square E is equal to j omega mu sigma into E. Let us assume that I have a metallic surface. Okay, this is air from which I have some wave coming in. Okay, and then there is a region that is sufficiently thick metal is kept, and then the waves are actually coming and impinging on this metal surface. Okay, so once the waves come in and impinge on the metal surface, there will be, assume that this wave is actually a plane wave. So which means that it has x component for the electric field and y component for the magnetic field, and the wave is propagating along z direction. What I am choosing in this particular coordinate system is to consider z less than 0, that is negative values of z to be metal and positive values of z to be air, and then this is how the z axis is going. It is actually going from metal to air, and the wave is going from air to metal. Okay, what will happen? As the wave impinges, there will be electric field lines, right, and these electric field lines will be along x axis. Let us assume that the surface is kind of uniform along the xy plane. Therefore, their entire electric field lines will lie on xy plane, and they would all be directed along x axis. Okay, they would be uniform at a given z equal to 0 plane, and they would be pointing along x axis. Okay. However, as you go deeper into the metal, you will see that these lines of j vector actually start to become small and small. Okay, so these are the electric field lines, and the blue colors are the j lines. Okay, this electric field at the surface will induce a certain surface current density, and this surface current density actually goes exponentially decays. Okay, so this current exponentially decays inside that of a metal surface. Okay, and how do we describe that one? Well, for region z greater than 0, that is for air, the electric field is described by this wave equation. Okay, however, for z less than 0, where you have the wave converted in the form of the current density lines, this equation needs to be changed. So for z less than 0, that is in the metal surface, I want an equation for j, not for electric field. Okay, so what is the relationship between the two? I know that E is given by j by sigma, so I can substitute for that E. Okay, so when I substitute for E, I get an equation for j as del square j is equal to j omega mu into j. But I already know that electric field was propagating originally along z direction, it was polarized along x direction, and since E and j are having the same polarization, I can replace this del square j by d square jx divided by dz square, right. This is obvious because electric field is along x, therefore j must also be along x. This is equal to j omega mu sigma jx. Okay, so I converted this vector equation into a simpler scalar equation that tells us how the current density vector jx is actually changing or actually propagating as you go deeper into the metal surface. What is the solution for this one? The solution for this equation is very simple. Jx of z is equal to Jx of 0, this is the value of the current density at the surface, which will be given by the applied electric field Ex of 0, right, divided by sigma, okay, and inside the metal this would be going as e to the power kz, where k is square root of j omega mu sigma. Therefore, this would be 1 plus j z by delta. Okay. Now, you might be surprised, why do I have a 1 plus j into z, what happened to the minus sign, and you should remember that this expression is actually valid for negative values of z. So, rest assured your j vector does not grow inside, j vector actually decays, right. So, you do not have a situation where at the surface you have a certain j vector, whereas at a certain later stage you have a j vector which is actually grown. No, what you have is only wave which is, j vectors which is actually decaying exponentially, okay, and this decay rate is again given by that skin depth delta, and the only thing is that this expression will have a plus sign out there, okay. Associated with this Jx of z and this Jx of 0, there is also another quantity called current per unit width, okay. What is this current per unit width? Imagine that I have these j lines which are going like this, right. So, this is how the j field lines are all going, this is the x direction which I am taking, and then this j lines actually start to decay in amplitude and eventually reach to 0 down below. So, after a certain amount of depth they would actually be very close to 0, right. So, this is how the electric field lines are all, and then they would actually reduce their amplitude and then go to very small values inside the good conductor. Now, what you do is you consider a integration, right, along y axis. So, my fingers are pointing along x axis, okay, this thumb is supposed to be pointing along the z axis, and therefore, I have this direction to be the y axis, okay. So, x, y, well, the other way around, okay, the y axis should be coming out to me like this. But the point here is that I have x and I have y, okay, and if you look at an integration of these j lines in this area which is given by this say some meter, 1 meter along y axis, and then going all the way towards infinity along z, coming back from infinity and coming up. So, you actually have a loop, okay, through which the j lines are all piercing out, and then this loop has a width of 1 meter along y axis, okay. So, in the yz plane consider integrating this j field to get, so integrate this Jx of z to get what is the total current, okay. So, this I am going to get as the total current, but so total current I, okay. However, integration along y, because Jx is a function only of z, therefore, integration along y gives you 1 meter, and if you divide this integration along y, what you get is current per unit width, which is given by integral from minus infinity to 0 Jx of z, okay, dz. This will be a vector directed along y axis. This is the current per unit width directed along y axis, okay, and this is given by integral from minus infinity to 0. This is Jx of 0 e to the power 1 plus j into z by delta dz, and when you integrate this one, what you see is Jx of 0 into delta divided by 1 plus j. What is the meaning of this? The meaning is that the current per unit width is actually out of phase by 45 degrees with respect to the current in the surface, right. Current on the surface Jx of 0 is 45 degrees out of phase with the current per unit width, okay. So, this is the meaning of this. So, IW is 45 degrees out of phase with respect to Jx of 0, which is the current at surface of the conductor, okay. So, this current per unit width IW, which we have found out, actually can be very useful for us, okay, because IW has units of ampere per meter, okay. IW has units of ampere per meter, okay. Now if you look at this Jx of 0 and relate it to the electric field, okay. So let me write down this one. IW is given by Jx of 0 into delta by 1 plus J, okay. I know what is Jx of 0, this is the surface current density at the surface of the conductor, which must be equal to sigma times electric field component Ex of 0, right. So substituting that, what you get is IW is equal to sigma Ex 0 divided by 1 plus J, okay, and there is a delta out there, so sigma delta by 1 plus J. Now this quantity Ex of 0 has units of voltage or volt per meter or volt per unit length, and this fellow has units of ampere per meter, right, because this is current per unit width. So if you take the ratio of voltage per unit width to current per unit width, what you will get is something that would be impedance, right. So if you take this ratio of Ex of 0 to IW, what you get is 1 plus J divided by sigma into delta, okay, and this actually is a complex number, Rs plus Jxs, or I can write this as Zs and call this as surface impedance, okay. Surface impedance is actually telling you that electric field E at the surface to the current per unit width IW, and this ratio is the surface impedance, and clearly you can see that this ratio is not real, that is, it is complex, indicating that Ex of 0 and IW are out of phase by a certain factor, okay, and because of this out of phase thing, the total power carried will not be exactly equal, only a part of the power will be carried by the wave and the rest of that power will actually be lost to us. So this is what we wanted to write. There is the last matter of actually calculating how much power is getting lost, okay. To calculate the power loss, first consider a scenario, okay, which we want to write down in terms of the voltage and the current, right. So this is my x axis, okay. So all the J lines are all being uniform, right, on this x axis. Of course along Z they would actually be decaying, and then I have a y axis up here, okay. Now let us assume that this width is W, okay, and this length which I am considering is L, okay. So there is a width of W along y axis and a length L of the conducting surface that I am considering along x axis. What is the voltage that is induced in this length L? Voltage induced will be Ex of 0, because this is at the surface I am considering, times L. What would be the total current I passing through this width W? That would be IW into small w, right, that is the width here. So current per width into width will be the total current. The ratio of V by I is given by Ex of 0 L by W divided by IW, right. Now Ex of 0 by IW is something that we have already written down. This is nothing but Zs, and then there is a factor of L by W. What happens when you consider L is equal to W? What you are really considering is that of a square, okay, whose area is W square, whose sides are W and W, okay, and numerically V by I will then be equal to Zs. Because of this reason, this Zs is actually called as surface impedance, okay, per square, right, because when L is equal to W, the ratio of V by I, Zs, which is in the form of ohms, will be numerically equal to the ratio of V by I, and this would happen only when L is equal to W, which is when you would actually have created a square. Therefore, if you call this Zs as impedance per square, okay, or Rs as resistance per square and Xs as reactance per square, then multiplying by the square you are going to get the total impedance, okay. So this is what we wanted to write. Now for the matter of the power that is lost, we know that the average power for complex V and I, that is phasor quantities, is given by half of real part of Vi complex conjugate, right. Now I know what is V, I know what is I, so let me write down those expressions here. So this becomes half real part of Ex of 0 into L, right. I is nothing but IW complex conjugate, W complex conjugate, right. I know that L and W are real, therefore they can be pulled outside. So I can write this as half area. So area times real part of Ex of 0 into IW complex conjugate. But I know that Ex and IW are related to the surface impedance Zs. So I will actually be able to write down two ways. One would be to write this as Ex of 0 and then write this IW square as Ex complex conjugate of 0 divided by Zs complex conjugate. Okay. Or there is another form which is I will substitute for Ex and write this as real part of IW into, right, IW because this one, and then into Zs there is an IW complex conjugate, right. So you can see that this form will give you half A, right. Ex0 complex conjugate is real, so you can pull this one outside, so you get Ex of mod 0 square and real part of 1 by Zs complex conjugate, or equivalently you can write this as half A IW into IW complex conjugate is nothing but IW magnitude square and real part of Zs. Now real part of Zs is nothing but Rs, therefore this is given by half area IW magnitude square into Rs. This would be the average power, but if you are interested in power per unit area, that would be obtained by dividing the average power with area. So you get half IW magnitude square into Rs. There is one last matter which I want to discuss, in which I am going to relate this IW to the magnetic field. Okay. This expression will become very useful for me when I relate the current to the magnetic field, because then it will allow me to calculate the losses of waveguide walls, how much power is getting lost inside a waveguide wall. You can also extend that analysis to any other metallic surface. Okay. So what we want is now relationship between, right, IW, which is current per unit width, and magnetic field H. In order to get this one, I will invoke Ampere Maxwell law. So I have H dot dl being equal to integral of J dot ds, and I know for this case that if I consider this one as say y axis, this as z axis, and this as my x axis. So hopefully all the directions which I have written down are correct. Okay. So on the surface, if you look and form a path of integration, okay, which is having h units, okay, along y and having d unit along z, where we are going to assume that d is much larger than skin depth, so that the fields here down in the metallic surface are actually almost 0, and we consider the path in this way, okay, going along the segment 1, segment 2, segment 3 and segment 4. Now this integral of j dot ds we have already written down, right. So this is nothing but integral of j dz, jx dz and dy, right. But integral of jx dz is something that we have already written down. This is nothing but the current per unit width, and times integral over dy will be this integral over h. So this would be IW into h, right, h being the width along the y direction. What happens to the left hand side? Well, for the case of plane wave that we have considered, h will only have y component, and therefore segments 2 and 4 will not contribute anything, because in these segments h is along y, but the line element or the line integral is along z, so there won't contribute. There is no contribution of h in the segment 3 also. Why? Because h would have decayed so much because of the skin effect thing. The E values and H values at depths which are much larger than skin depth would actually be almost 0. Therefore, H contribution along segment 3 will be nothing. Therefore, the only contribution of H is that of the segment 1, at which point I have minus H y into small h is equal to IWH. Therefore, this gives me IW is equal to minus HY, or if you consider a normal along the metal surface outside to the metal surface, right, this can also be written as n hat. So this normal, if you consider, then it can be written as n cross h, okay. H is along y and n is along the surface z. So you have z cross x, that is what the direction for IW would be, okay. So regardless of the fact, on the surface this HY is nothing but tangential component of magnetic field, right. Therefore, what we have here is the current per unit width or the current on the metallic surface is actually equal to, at least the magnitude of that one is equal to the tangential H component. Okay. You can now substitute this expression for IW into the power lost per unit area and obtain the power lost per unit area is half HT, where HT stands for tangential magnetic field magnitude square times RS, and RS is something that is determined by the material properties. It is actually sigma dependent, the conductivity dependent. HT magnitude square is actually dependent on the magnetic field that is induced on the surface. Okay. So, this expression for power lost per unit area is very important, and you should keep this expression in mind when we later discuss waveguide losses. Okay. There is one other concept associated with wave propagation inside that of a imperfect conductor or a dielectric. The question is, how do you consider which one is a conductor, which one is a dielectric, and this can be considered by considering the ratio of how much conduction current is there to the displacement current. Okay. And this ratio of conduction to displacement current is actually captured by what is called as loss tangent. Okay. What is the total current inside that of a material when there is conduction as well as displacement current? You have conduction current given by sigma into E, right, and the displacement current is given by j omega epsilon E, assuming that electric fields and all the other field quantities are going as e power j omega t. So, this is the conduction current, this is the displacement current. You can actually plot them on the x and y axis. So, I can actually plot this one as the displacement current. This will be given by j, or in terms of j this would be omega epsilon, and the magnitude of the conduction current I can plot here. Okay, this would be the conduction current which is given by sigma into E. Okay, and then the total current is actually the vector sum of these two. So, if you assume that these two are the two vectors, then the total current will be of the vector. Okay, and it would be making an angle of theta here and an angle of theta prime with respect to displacement axis, right. So, what is this angle? This angle theta can be obtained by looking at what is tan theta. Tan theta is nothing but omega epsilon divided by, so do not worry about this j. So, you just look at what is tan theta over here. Okay, for 1 second let me actually call this as theta and call this as theta prime. So, tan theta prime is omega epsilon by sigma, because electric field on both sides will actually cancel, right. So, this both sides will actually cancel. Okay. Or if you measure theta with respect to the displacement axis, which is what more commonly is done, then tan theta is given by sigma by omega epsilon. Okay. And this tan theta is what we call as loss tangent. Okay. Why is it called as loss tangent? If you look at two cases, okay, in one case let me assume that the conduction current is very large, okay, and the displacement current is very small, then the total current actually points very close to conduction current, and theta is around pi by 2. So, this would be the case when tan theta is getting very large, right, because theta is becoming pi by 2. So, therefore, tan theta is very large, which means that there is complete loss, because sigma is much high, right. Then the propagation constant, as you have seen, attenuation constant as you have seen, will depend mainly on this sigma, and it would be very lossy situation. Okay. So, this is your conduction current and this is your displacement current. Okay. On the other hand, if the material is a very good dielectric and having very little amount of conducting losses, then that particular material will have no attenuation. So, this would be the electric field which is very close to this one, and the angle theta will be very small, implying that theta is small, right. So, theta is approximately 0. So, in this particular case the wave will actually be propagating without any attenuation, and this is a case where you do not have any loss, or the loss is very small. Okay. So, depending on which one is larger, you can actually consider this as dielectric or as a conductor.